morning, friends. I welcome you again in my course Aircraft System. My topic of the day is 270 volt direct current power system on aircraft. I am Dr. Dwivedhi, professor from Institute of Aeronautical Engineering, Hyderabad, India. As you know that I have started this course and today I am in the lecture number 13. Before that, I was there in my module 1, and in that I have covered my basic introduction of aircraft structural system, airframe system, aircraft vehicle system, avionics system, and mission system. I have given the brief idea of these all systems, and all details of these systems are covered in this coming. In this module 2, I am covering now electrical system, and after that I will be going for the air conditioning, then after that firefighting and all other systems I will be covering. So in my today's lecture, I am going to take introduction of 270 volt DC power supply, advantages of 270 volt DC, 270 volt power converter, 270 volt DC bus in the VSCF aircraft power system, 270 volt DC power converter designed for the 270 volt DC. So I will go first the revision of my some previous topics. So if you see that I have discussed about the power generation system, in that the CSD, then IDG, integrated direct generator, and the constant speed drive, then TRU, and I have also discussed about emergency power supply. So in this emergency we have the APU, then battery, then RAM air turbine. These are the three which are used for the emergency power supply of the systems. I have also discussed the different power generation devices, how these things are working. These all things I have already covered, and now I am going to see a new topic which is 270 volt DC power supply. I want to say this thing, that this 270 volt DC is only used in some American aircrafts, especially the modern fighter aircrafts like F-22, F-33, F-35. However, this 270 volt was also used in submarines very long back. From there only they got this idea, and they have implemented this idea of 270 volt DC in our aircraft. So I will go first with the introduction, and then you will enjoy this idea of 270 volt DC. In earlier classes, I explained why aircraft and most military equipment was powered by 400 hertz or cycle power. I have explained in detail why we need the 400 hertz cycle. Just I will give some glimpse that if you are using the 400, the weight of the aircraft is reduced. Weight of the electrical power generation is reduced tremendously. The weight of this, if it is reduced, then what will happen? You know, this weight is the very important parameter in any aircraft. How much we are able to reduce the weight. So if you reduce the weight, the engine thrust required is reduced. So if the engine thrust is required, you know that once the aircraft, how this thing, this is the aircraft, this is the lift, this is the weight, this is the thrust, and this is the drag. So this weight is very important. So if you reduce this weight, lift is also required, lift is also reduced. And as this lift is reduced, thrust is also reduced. Okay, so as much you are able to reduce the weight, that much cube of thrust is reduced. Once you reduce the thrust, the fuel consumption is reduced. Fuel consumption is reduced. So as the fuel consumption is reduced, for a given weight of fuel, range and endurance will be more. For a given amount of fuel, your mileage, like your mileage of your bike or your car, the fuel consumption of your aircraft is very important parameter, and especially for the passenger aircraft, if we are able to reduce the weight, that much fuel is reduced and the cost of operation of the aircraft is tremendously reduced. So that matters, and we as engineer, we should try to make some arrangement so that the aircraft weight is reduced. In this connection, the 400 Hertz frequency of power is used in aircraft, and we have discussed in detail, and this mainly all the wires, very thin wire we can use, the generators, the size of the generators, power generators also can be reduced. And if you take the total amount of this by using 400 Hertz, a huge amount of weight we can reduce. So this included the statement that this standard was worldwide. So this 400 Hertz is used in all over the world, and every aircraft equipments are operating under 400 Hertz. Wherever you fly, there will be a 400 Hertz power source available with a standard plug that fits your aircraft. All over the world, it is almost in all the countries, all the aircrafts, they use 400 Hertz, and their socket, which is male and female socket, which gives the power to your aircraft. All over the world, every airport, they will have same type of trolley where you can plug in and get the power supply for your aircraft. Well, almost there are a few exceptions. Smaller and older aircraft use a 28 volt DC system, and smaller airports may only have a 28 volt DC power sources. However, the older and very small airports, they may not have 400 Hertz power supply, they will have only 28 volt DC supply. During the last 16 years, there has been a growing usage of third system. So either we have used 115 volt DC, 400 Hertz AC, 115 volt 400 Hertz AC, or 28 volt DC. But from the last few years, a growing tendency of 270 volt DC has been developed. The 270 volt DC system for aviation was first defined in Military Standard 704B, that is on 17th November 1975. So in this, they have given some standard of this 270 volt DC. Battery system in this voltage area had been utilized in submarine since 1900. I told you before also. So in 1900 century, I think more than 200 or 300 years, 200 plus years, in submarines, they used to have this 270 volt DC. Advantage of 270 volt DC. Just I will explain here. Very important that we have to understand that what is the use of and what are the disadvantages also. It is not this everything is positive only. If you want to take something, you will lose something. So the old reason for the 270 volt system was increased power density and the capacity. So the first and foremost, increased power density and the capacity. Means per unit weight, the power development is very high comparing to the other system. The new interest is due to the stealth. Another very important is the stealth parameter. If you use the 400 Hertz, this frequency is not good for the stealth characteristics. Your sensors of enemy sensors of radar, they will try to detect this type of frequency because it generates a heat, and that is able to detect by the enemy. Concerns and design changes in modern fighter aircraft. Okay, so this stealth also want 270 volt DC, and design changes in modern fighter aircraft. Alternating current system such as 400 Hertz are not as stealthy as direct current DC. So this 400 Hertz are 115 volt AC. We use 115 volt AC, 400 Hertz. We use this power supply. They are not stealthy, means they can be detected as direct current. The modern aircraft like FA-22 Raptor and the F-35 Lightning require a system that is more precise. So they are very precise system, these two aircrafts, and has a faster response and is tailored to the specific requirement of the aircraft manufacturer. So these two aircrafts are using, few more are there, and all are the US origin aircrafts only. They are using this 270 volt DC because it gives very precise and it is very fast response. Electrical signals are going very smooth and it is also trying to avoid the circuit problems and fault diagnosis. These all things it can avoid. Advantage: the previous generation of fighter aircraft used a dual hydraulic system to move the flight control surfaces. This presented a large vulnerability should the aircraft suffer damage and fluid loss. So what happened now? This in olden days, most of the aircraft used to operate the hydraulic system, and there is two hydraulic systems to move the flight control surfaces. You see how this flight control surfaces used to move. Just I will show you here. This is the aircraft. These are the wings. This is the tail. Here is the elevator. This is the elevator, and here is the rudder. This is and here we have the ailerons both sides. So these are the flight control system. So what happened? Here we use the dual hydraulic system. So here we will put a jack here. Here you see. Here also we will put the hydraulic system. They are the hydraulic jacks or hydraulic, and here also we will put some hydraulic jacks. So as the pilot operates from here, it will move the stick up and down. It will give signal to this hydraulic jacks, and this hydraulic jacks will move the rudder left or right. Same way, aileron left or right. Same way, elevator left and up and down. So what happened now? This dual hydraulic systems to move the flight control surfaces. This presented a large vulnerability should the aircraft suffer damage and the fluid loss. So if these things are operating, so mostly they may get damaged, and this should be very much large vulnerable for the flight. And the loss of fluid, if your line is broken, your loss of fluid will be there. Naval aircraft now utilize multiple electrically driven hydraulically actuator at each control surfaces. So nowadays, what happened? These jacks are electrically operated. If the hydraulic system fail, electrically will operate the actuator at each control surfaces. This now requires the electrical system to respond to a rapid load changes while maintaining the constant voltage. So here, as and when we change, the load will change, and if the load is changing, but voltage should remain constant. So this type of issues which we have to tackle, we have to handle this type of situation. Radar system requires more pulse power. Every aircraft has the radar, and since radar need a more pulse power while the voltage stay constant. So voltage should remain constant. However, this radar and all, they will generate the power. External power supplies are tested for voltage stability and recovery at various load configurations, transitions, and pulse loading. So external power supplies are tested for voltage stability and recovery at various load configurations, transition, and pulse loading. So these things we have to understand, and we have to see that these things are working as per the required voltage, and the voltage should be stable and it should be able to recover at various load configuration, transition, and the pulse loading. So these are things we have to maintain, and in this the 270 volt DC gives a better solution for this issues. Now 270 volt power converter, this you can see this figure here, how this power converters are working. This is FCS, the company name is FCS, and these are the devices which converts from AC to 270 volt DC. The performance of FCS system, that is 270 volt DC power in flight line and production line, proven for 270 volt DC from the ground up. Installation sites include main production and test site such as Lockheed Martin F-35 assembly in Fort Worth, TX, Navy F-35, T&E, NAS, River MD, and these are the best equipment is the preferred as the best power of choice for all 270 volt DC application. I think in world, this is the only company which is making this 270 volt power converter. Okay, so here 200 volt DC bus in the VSCF aircraft power system. This you can see here that a constant current load is here, and this is constant voltage load. Here there's two things are there. This load here, constant current load, and here is the constant voltage load. Both types of loads, and 270 volt bus. In this you can see that so many IREF is coming from here. It is going to the different systems, and then there are so many coils and resistance, capacitance, all the things, and then they are going to the main system here. Same way here, constant power load. So here three loads are there: constant power load, constant current load, and constant voltage load. So all the three, here is the P1, here is the P1, and here is the P1, and here there are some coils, and this will make sure that you will get a constant voltage load. So like this circuit we have to design, and we try to make this type of system which is used in aircraft for the 270 volt power supply system. Now we should see that 270 volt DC power converter, how it is converted. So this is the case of a conventional, and this is the 270 volt DC converter. So shows a full shell fed grid on modern aircraft with different load types. This is the conventional converter, and if you see here, this is the generator, onboard grid, cabin and the cargo. It supplies 360 to 800 hertz. Okay, but as and when it is going and it is changing to the different load, DC, AC, variable frequency AC, variable frequency AC, and this is the DC. So here we have different types of converters in a normal operation or conventional. It is called the conventional, and here we have different loads. This you can see here, 1, 2, 3. We have different loads here. So if you see here in the 270 volt, you see these things are same here. Okay, cabin and cargo, onboard grid. But if you see generator, variable frequency, alternating current, here it goes to 3 phase. From here it is converting to the 270 volt DC. Here is flight controller and here onboard grid, and from here it goes to again 400 hertz. It can be converted to 400 hertz as required. Okay, but here if you see 360 to 800, but here we want a constant frequency we want. Otherwise, I have explained that if the frequency is not constant, it will create a huge problem, and there are likely that some system may be able to get some problem. So now converter design for the 270 volt DC more electric aircraft. It is called the more electric aircraft. So the more electric aircraft, modern aircraft design is largely motivated by a desire to reduce the weight of the aircraft. So why we have to try to reduce the aircraft? So that is the aircraft design is motivated towards the reduce the weight of the aircraft, improve the power efficiency. Improve the power efficiency. The efficiency of the power should be increased. Reduce the engine emission. Fuel consumption should be reduced. Fuel consumption should be reduced. The first two of these can be achieved by moving towards a more electric aircraft. So if you are able to handle these things, reduce the weight, improve the power efficiency, reduce the engine emission, then it is called the more electric aircraft. And MEA requires increased power capacity requirement. So what this thing is required? It is more capacity, new power distribution system with higher voltage and being proposed, and 270 volt DC is preferred. What is the motivation here? Why we want that type of more efficient, more electric, more electric aircraft? The Airbus A380 high voltage AC based electrical power system currently interfaces a Rolls-Royce Trent engine, electronic engine controller, that is called ECU, EEC, to the 115 volt DC bus. So it is 150 DC buses in Airbus 380. In the future, it is anticipated that the electrical power system will be 270 volt DC. So as of now, we have this power supply in Airbus 380. In future, this will be added 270 volt DC. Rolls-Royce currently have no DC converter for use with a 270 DC bus. So currently we don't have the DC to DC converter from 270 volt DC bus. They wanted to start investigating the design and development of a such converter. So they have studied. So it is a case study I have taken here for the DC converter. So what was the project? to investigate if it is possible to design and build a DC-DC converter to interface a Rolls-Royce EEC to 270 volt DC aircraft electrical power system using currently available component electronic engine controller. So this is shown here, electronic engine controller. This is the electronic engine controller of Airbus 380. A mid to low power electrical system subsystem 150 watt to 200 watt. A mid to low power electrical subsystem 150 watt to 200 watt. So what are the issue here? The electronic engine controller is placed in a non-temperature controlled, non-pressurized environment. Derating of components will be the biggest hurdle in finding appropriate component for the designed DC-DC converter. So these are the electronic engine controller EEC is placed in non-temperature controlled, non-pressurized environment. Derating of components will be the biggest hurdle in finding appropriate component for the design of DC-DC converter. So what are the performance specification we require for this type of DC-DC converter? Provide a DC output voltage of 48 volt nominally with a maximum tolerance of plus minus 10%. Ensure the output startup time is less than 10 meter per second. Have a maximum output ripple voltage of 500 millivolt peak to peak. Ensure transient due to load changes are less than 20%. Ensure that transient due to input voltage transient plus minus 50 volt are less than 5 volt. Under a fault condition, the maximum output voltage should be limited to less than 100 volt DC. The maximum in rush current shall be less than 8 volt. So these are the desired performance specification. Half bridge converter. So we have to use some converter. So this is the original choice which is everyone is using, and but decided current mode control was better option. So this one was the better option. So in place of this, they have used some NP1, D2, C2, D1, C1. Okay, and here if you see, there is a difference between this and this. Okay, so this system is suggested to do better performance. Okay, so that is the objective of this case study. So in this original choice is this, but as per this new thought, if you make like this, it will give a better control, and it is a better option to convert 270 volt DC. Here step down transformers are used for this thing. As you can see here, that primary 24 turns, 2 strands of 1.003 millimeter of wire here, and here DC restoration 25 turns, 1 strand and 0.805 millimeter of wire. So if you go here, output 1, here 8 turns, 2 strand of 1.389 millimeter of wire. Output 2, 8 turns, 2 strand 1.389. And in this, if you see feedback 1, here 5 turns, 2 strand 0.419 millimeter of wire, and feedback 2. So here is output is here, output here, here is here the feedback. And a turn ratio of 25:8 was chosen, reducing the input voltage from a maximum input of 297 volt, that is 270 volt plus minus 10%, down to 95.0804 volt. The PWM gate drive from controller IC regulates this, so 48 volt appears across the output. Okay, so this generating the 95, but it is shown as a 48 volt DC generator. So this you can see, layer 5 turns DC distortion. It is yellow color is DC distortion. This is the primary. This is the output 2, and this is the primary. This is the feedback. Red color is feedback. So layer 6 25 turns DC distortion. Layer 5 10 turns primary. Layer 4 8 turns of secondaries. Layer 3 8 turns of the secondary. This is shown how many turns are here. And layer 2 7 turns primary plus 4 turns feedback. 8 turns primary and 6 turns feedback. This is in the core of this system. So in this way it is designed, the step down transformer. Now simulated DC-DC converter, its results and all, it is simulated by Symmetrics 6.10 was used to investigate the DC-DC converter ability to satisfy the performance specification. Startup response is 1 millisecond, and this you can see that how these things are going, and it is improved by this new system. This is the improved efficiency. This you can see, this one is used, this one is used. So this one gives here this better efficiency. Okay, and so here if you see here, loss of feedback signal, converter output increases to maximum 80.18 volt with load current of 1 ampere. So this can be seen in this diagram how these things are working to get this work done. Now I am here the redesign to reduce the in-rush current. Initially designed in rush current is equal to 100 ampere, which is greater than 8 volt. Second iteration, introduction of TR13, TR14, which are turned on steadily during startup. In rush decreases to 5.8 ampere, but high stress on TR13 and TR14. This you can see here that how these fluctuations are happening in this diagram, 0.5, 1 and 1.5, and after that it is going here as a smooth. It is changing here in this direction, and this all parameters are mentioned here, that how many amperes and how much this TR13 and TR14 are working. So in my next class I am going to discuss about the air cycle system for air conditioning and the pressurization. Here first I have the basic cycle, second I have the vapor cycle, bootstrap cycle and the evaporative vapor cycle. I will be discussing in these topics in my next class. Hope you have understood, and as of now I have completed the electrical system of module 2, but still I am in module 2 only, and I will be discussing this, and you will be enjoying this, how in the real aircraft we are getting the air conditioning and the pressurization, and it will be very nice to listen. It will be very good and very fruitful for all. Try to attend this my next class also. It will be good. I'm using my references, that is the first one is Moyer and Seabridge, aircraft systems, mechanical, electrical and avionics system. Then the second book I am using, Design and Development of Aircraft Systems and Introduction, AIA Education Series, AIA 2004. Here I am now very near to the end or almost end of today's class. Any questions, any queries, you are welcome to ask in my given email. My email I give in every my class. I am yd dwivedhi@gmail.com. You are welcome to ask any questions in this, and hope you have enjoyed my this class. Please be tuned for my next class. Thank you very much for joining. See you again in my next class. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.